On this entry of the STEM journals, mechanical arms, legs and hands, and my biking motion tracked and captured in Biomechanics. Author, musician, meteorite hunter, adventurer. I've led an eventful life. Now I'm exploring exciting STEM careers and recording what I find in the STEM journals.
STEM journal, initial entry. I've often wondered about the human body. Why is it that I've got 2 legs and most of the animals around me have 4? And how exactly do we kick a ball or whip up eggs for breakfast? I mean, I know it has to do with the structure of the human body and how muscles and the skeleton work together, but what's so special about all of that? Well, I'm going to find out, because I've offered myself up as a human guinea pig to Aaron Ross at the Faster Fit Lab. This is a most impressive place. Oh, it looks like a rocket. What is that?
That is a water bottle.
Oh, impressive. Okay, well, I don't know what you've got in store for me, Aaron, but I am your test subject for the day. So what is the plan?
So first thing I'm gonna need you to do, put on these clothes and meet me in the Fit Lab.
I will do that. Okay, Aaron, I'm ready for action and I feel like the running man. What do you think?
Well, first I'm gonna need you to ditch the vest.
Sorry, I never go anywhere without the vest.
Well, in this time, we're gonna have you wear this vest so that we can use our technology.
Okay, I'll make a special exception for you. Okay. Important to note that these are not called sensors, they're called markers, which means I am a marked man. This is my new superhero costume. What do you think?
It's pretty good. First I need you to pop on the cap.
Ah, splendid. Aaron, you have possibly the most impressive job title I have ever heard, and that is Faster's Biomechanic Aerodynamic Fit Specialist. How do you get a title like that?
Well, I work in bike fitting and I spend a lot of time in our wind tunnel. So I have to have a really good understanding of what is happening biomechanically with the body so that when we go into the tunnel, we can make accurate changes and make a person faster while pedaling very efficiently.
I gather you're going to digitize me somehow.
We are.
That's what all these markers are for.
We will make you come onto the computer. We got 34 and I'm gonna grab them. Got them. And you can go ahead and take a seat on the bike.
I'm an avatar in the system. Getting on the bike. Aaron, I'm thoroughly enjoying wearing this real space-age suit, but why are these markers in such specific places?
Well, we have them in specific places in order to create the avatar on the computer. We're going to be able to track certain parts of how you're pedaling, and we're going to be better able to analyze how efficient you are and what changes we may make in order to make you more efficient or to fix a issue. If we're more random with the placement of the markers, our angles and the data that we'll be receiving will be inaccurate as well. Because the system is all calibrated, all these cameras know what their angles are, the distances are, we can be very specific on our measurements.
We're seeing a very sharp image of me there on the screen. What's it telling you?
Well, for instance, we can go in and we can look at how the equipment of a bike and a rider are interacting together. All in all, the end effect is we're trying to make the cyclist pedal down the road comfortably, efficiently, and have a lot of fun while doing it. The bike will basically become an extension of them.
Okay, I understand what the markers do. I understand what the software does. But as an expert, what are you learning by looking at the mocap?
We're learning how the rider is pedaling, and sometimes we have to look at and help retrain the cyclist to better interact with their bike. If somebody is pedaling in a certain way or their equipment is not working for them, this can lead to injuries down the road.
So you're not just making more competitive athletes, you're making safer, healthier cyclists.
Safer, healthier cyclists.
I like that.
Yep. In addition to that, we can take a shorter video and move around the rider so that the rider does not have to get so tired riding the bike in here. And I'm going to record you riding, and we don't need to take a super long video, so typically I take about 10 seconds. And now we can go back in and edit it. You can relax there, Geoff.
Oh, with pleasure. I feel like I've been cycling for a long time, but not going anywhere.
We can see the motion of, for instance, your foot here and see how clean the circles are. You know, if we see any excess wobble, we know that there is some efficiency there. If we look at your knee, for you, we can see that we have, on your upstroke, your knee kicks out. So the efficiency of that is not very good, and that over a period of time will probably cause an injury. This information here allows us to do a comparison when you come back in the future so we can see how the changes we've made and how you've adapted to it, and then we can make better changes in the future, if need be. In addition to that, scientists are using this in robotics to help build a better robot based on the human biomechanic.
Now you're talking my language. In fact, my next stop is the robot lab.
Why on earth are mechanical engineers trying to get a grasp on the human hand? I explore next on the STEM Journals.
STEM Journal, supplemental. Well, I'm still quite tired after my workout at the Fit Lab, but who cares? I'm visiting a completely different kind of lab to speak with Dr. Veronica Santos of ASU's Biomechatronics Lab, where she and her team are giving humans a hand up on their research. It's biomechatronics, not biomechanics.
Yes, like biomechanics plus mechatronics all smashed together.
All smashed together. Biomechatronics. I love it. Excellent band name.
Yes, yes.
This is actually a mechanical engineering lab.
It is.
And when we think of mechanical engineering in the day-to-day, we might think bridges, airplanes, but you're doing something a little bit more unusual here.
Yes, actually the mission of our lab is to improve quality of life by enhancing artificial grasp and manipulation. So we study human hands, robotic hands, prosthetic hands, and tactile sensing, and that requires a lot of different backgrounds, including mechanical engineering.
So what would be some of the practical applications of the mechanical parts that you're devising here?
Well, one of the applications that I'm personally most interested in would be advancing neuroprosthetics, so prosthetic arms and hands for amputees, but of course this can be used to enhance any type of system where you have humans and machines coming together. So you can imagine maybe a teleoperated robot going out for search and rescue or bomb defusal, but the idea is a human trying to control a machine to physically interact with things in the world.
I have to tell you, Veronica, I'm no stranger to mocap because I did some work at Faster, and I'm assuming we're using very small markers here because you need more precise measurements.
Yes, the hand has so many different segments that we're interested in tracking that we have to use smaller markers in order to put so many on the hand. We can track with our camera system the location in 3D space of each of those markers, and then we can color code each of your fingers and study how your digits are coordinating themselves when you do different tasks, when you're pinching things, grasping objects, pouring liquids out of containers. We're very interested in how fingertips are coordinated.
So in other words, you would record the data,
Yes.
and then you would theoretically be able to recreate the motions that I made
Yes.
in one of your robot hands and arms.
Yes, we can actually take the locations of these markers and using math, figure out what the posture is of your hand, as well as the joint angles between each of these different segments. Most commercially available hands, whether they're robotic or prosthetic, actually do not have tactile sensing, which is exactly why we're building the Bear Claw in our lab. This fingertip can actually sense temperature, force, and vibration.
So you're telling me I am looking at a robot finger that can feel that fabric?
Yes.
I'm clearly super impressed by the technology, but what's the point?
Well, reach into your bag without looking and see if you can tell me what you've got in there.
Okay, without looking, I can tell you that I have in this bag my STEM journal.
And how did you know that?
Because I can feel its shape and its unique features.
Yes, you can feel probably the texture, the edges, and you already have an idea of what that object feels like. Imagine an amputee or someone who's teleoperating a robot for search and rescue needing to actually feel what they're interacting with. So for example, activities of daily living. When someone needs to wrap a belt around themselves or reach behind something to find a button without looking, things that you and I take for granted with the sense of touch someone could do.
Wow, you don't even really think about that. Or like reaching in your pocket for coins or in the dark reaching for a glass of water.
Not until you've lost that sensation
Yeah.
do you realize how critical it is to everything that we do.
And doesn't that illustrate what a fantastically advanced machine the human body is?
Yes.
So the next generation of engineers and robot scientists may be the one to build this technology and make it happen.
Definitely.
I want to see that.
Me too.
I have never in my life been able to say this before, but you have me wired to an actual robotic arm.
Yes, we do. We're actually going to do something of a prize claw type of task where we're going to control the arm motion. The hand is going to come over and you're going to flex your biceps to open that robot hand and then relax your biceps to close the robot hand. And we're going to have the robot arm pick and place the object for you.
Go, go, go! And it's a winner!
Yes.
Oh, fantastic. Okay, I only had one, you call it one degree of control, 1 degree of control. But there's a device that has 40 degrees of control.
Yeah, you can imagine this particular robot arm has 11 degrees of freedom. If I wanted to make the task more difficult, I could ask you to control all of these joints, including each of the individual fingers, to do that very simple task.
You know those films when the robot goes crazy and kind of smashes up the department store? That's what would happen if you gave me 11 degrees of control. I've enjoyed every moment of my visit to the Robot Lab. So thank you for that. And you get to do this every day.
We do, and you should definitely learn more about prosthetics, and you seem really excited about robotics, so definitely check out the Hork Lab next door.
Okay, I'm going to prosthetics, and I think I have just the person for the Hork Lab.
Still ahead on the STEM journals, I hit the ground running to learn about prosthetics and request Becca to log another robot entry.
All right, Becca, are you ready for your next young STEM investigator assignment?
I am so ready. I love a challenge, and biomechanics seems really interesting so far.
Excellent. I really like your enthusiasm. I am going to follow the advice that I was given by Dr. Santos and learn more about prosthetics by visiting the artificial limb specialists. I want you to spend your time here at ASU's Hork Lab and find out what they're really doing with robotics.
Geoff, nice to meet you.
Nice to meet you. That's a nice firm handshake you've got there.
It is. You're shaking the new iLimb. It's a myoelectric hand, so it operates off of sensors inside the prosthetic arm. So we're going to touch this outside, or touch that sensor there. And it's going to close it, and then the inside sensor is going to open it.
Now, this reminds me of something that I worked with at the Biomechanics Lab at ASU, where I controlled a large robotic arm when sensors were put on my bicep.
Correct. And this one is meant for everyday use so that they can pick up an object off a table or grab their luggage or hold their child's hand. This technology's been around for about 60 years now. It's a body-powered hook. And you can operate it by putting on this harness.
Thank you.
Sure. And go ahead and just flex your shoulder forward, and it should have the hook open.
Okay. So we're seeing traditional, cutting edge. Where will the technology have to go for the next generation of prosthetic designers to really make a difference?
Well, I think the areas that they're focusing on are sense of feel and sense of touch, implanting sensors in the hand and directly into our bodies so that when we grab down on something like our child's hand or an egg for that matter, they know how hard they're gripping down on it and they know if it's hot or cold. They're also working on thought controlled, so they're directly implanting things into our body so that we can just think about closing down and the handle closed versus right now we have to actually flex a muscle to get the terminal device or the hand to close down and open like we want it to.
And in your work, you've got quite a broad range of skills. You are fabricating the prosthetics, and you're also helping your patients become familiar with their use.
Absolutely. It's half art and half science. And the greatest part about my field is that I get to build something that helps somebody's life. So somebody goes through a tragic event, such as the loss of a hand, I get to meet with them, take an impression of their limb, build a device, put it on them, and watch them go and lead the rest of their life. It's just absolutely fantastic.
I work with a lot of people doing fascinating cutting-edge work, but if you want to see an example of modern technology really helping improve the quality of life of people, here it is.
Yeah, I love my job. It's the greatest profession in the world, in my opinion.
Seth, this is the literal wooden leg, and much like the replacement upper limbs that I've seen, I'm guessing this is not where the technology is today.
Not even close. This really was born in the Civil War era. And we've cut this one open so you can kind of see the inside. You know, the limb that was amputated would go in here and they would just make it all out of wood. finally, not until really in the 80s, did we start getting some newer components and some advancements, and we started using some softer foam materials, and you started to get them shaped and looking a little more natural, but you still had these bulky joints on the side and it would lace up your thigh. You know, we started getting into the really high-tech stuff, and there's been a lot of advancements recently, and we start to get to something like I'm wearing, which is a vacuum system, and really locks it onto my leg, and it feels like an extension of my body as opposed to something hanging off the end of it.
I find it fascinating that you have different limbs for different activities.
Yeah, they can get very activity specific. I mean, I have a different leg that I wear when I go to the water. I grew up on the beach, so I love to go back and go surfing, do wakeboarding. I've got my leg that I wear for every day, just being comfortable and being at work and living my life. Really, one of the cool parts of our field is that it's half doctor's office and half mechanic shop. The high-tech stuff, and especially the running feet, are kind of a really cool part of being an amputee. I've fit a lot of them on patients, but I've never actually gone for a run in one yet. So we've been working on a running leg for myself to actually get out and do a little running. I think we should go give it a test drive.
I must say it's a very impressive design, very, very high-tech. You look super modern.
Yeah. If you pay attention to the Olympics at all, they tried to disqualify the guys missing legs because they said it was an unfair competitive advantage.
Really?
So,
how about that?
Try and keep up.
Oh, all right. I don't think it's going to be possible. Talk about being a specialist. You're a CP and you're an amputee, and the thing that inspired you to go into this field professionally, you wanted a replacement lower limb and you just didn't think any of them were good enough, so you decided to go into the field and make a better one.
I got so frustrated that I just decided that, I was going to go back to school and get into the medical field and learn to do it for myself and do it better and help other people get back to those kinds of activities. And the change that's happened since then is enormous.
It's a remarkable story, and I think it's a very good commentary on life in general, which is the technology is not where it should be, and so I'm going to improve it.
Yeah, let's do
I like
something
that.
about it then.
It's really positive. All right, Seth, well, you beat me up pretty good today.
I'll hook you up with a trainer if you want.
Yeah, that's probably a good idea.
Get you a little quicker.
Up next on the STEM Journals, I catch a breather while our fearless young STEM investigator grapples with human-oriented robots.
Dr. Artemiadis, can I call you Panos?
Yeah, of course.
Panos, what is this you're working on right now?
So in the Hork Lab, we're working on controllers to interface humans with robots. If you think about robotics 30 or 50 years ago, robots were only used in industrial environment, essentially for jobs that require high accuracy and high speed of motion. However, in a few years from now, robots will be introduced in our houses. So what we want to build here is robotic controllers that will make our robots move like humans. So for that reason, we study kinesiology and human arm kinematics and biomechanics in order to really understand those principles of motion, the principles of you moving your arm, and then take these principles and apply them onto a robotic controller. So we essentially try to teach the robot to move like a human.
Panos, this is very interesting. Can you show me how it works?
Of course. So one of the projects that we are working on is how we can interface humans with prosthetic devices. So for example here, we are measuring the electrical activity from muscles by using those superficial surface electrodes. Jeremy here is activating his muscles and the robot is following this motion.
So we know that humans have 3 joints, the shoulders, the elbows, and the wrists, but this appears to have more than 3. Can you tell me what that is?
That's a very good question. So our human arm has indeed 3 joints, shoulder, elbow, and wrist. However, these joints are very complicated in terms of structure. We actually have 30 to 35 muscles only to actuate those 3 joints. So that's a very complex mechanism. If we want to replicate it at a robot, we need to make it as simple as possible. We have here a robot arm that has only rotational joints, only a hinge joint. However, we need to have 7 in order to meet the criteria that we want, which is to replicate the dexterity and the workspace of the human arm.
I think I'm starting to get the hang of this now. Now, you've earned your PhD in mechanical engineering, but you also understand a lot about human anatomy and physiology as well.
Well, our research field is highly multidisciplinary, so we need to learn a lot of things about human anatomy, human biomechanics, and neurophysiology. So we study a lot of neurophysiology in order to really understand how brain works and how brain controls our motion. And this is something necessary to do whenever you want to build and control a robot that really interface with humans.
I definitely learned a lot today. Between touring the Hork Lab and Geoff's journal entries, it takes a lot of work to duplicate the human arm into robotic form. Who knows? Maybe one day I want to study in biomechanics, become a physical therapist, or sports medicine, but I have to consult my teacher first before I go into those fields.
What are biomechanics? Well, first of all, biomechanics is creative. If you learn biomechanics, you could be a kinesiologist, you could get into robotics, you could be a mechanical engineer, or even make prosthetics. So what do you have to study to do that? Well, first, biology, also physics, and be sure you study mathematics. Ask a teacher. It all starts in the classroom.
On the next entry of the STEM journals, history is beneath our feet and tells a story of engineering marvels as revealed by modern-day Indiana Jones-like archaeologists. That's next week on the STEM journals.